And welcome everybody to Big Data for today. I'll start just by sharing my screen. And so here's on our GitHub repo on week 11 right now. And you can see up here that I've posted a link to our second Twitter Postgres homework assignment. And I've decided to make this assignment due not this Sunday, but a week from Sunday. So you'll have a little bit more time to work on it. We should have everything that you need for the assignment though covered today in class. And next week, there will be an additional homework assignment. It'll be hopefully on the lighter side of homework assignments, but it'll be sort of a written one similar to the week 9-10 homework that's due this Sunday. Are there any questions about any of those sort of admin details, due dates?
How do you want the week 9-10 homework turned in? Do you want to just send like a text document or a text submission in Sakai?
It's a good question. So as long as in some way it's clear, like problem 1, here's the answer, problem 2, here's the answer, then that's fine. So if that's easiest for you as uploading like a PDF that's been annotated, that's fine. If that's easiest for you, just writing it out as a text entry in Sakai, that's fine too. Whatever is, whatever works. Good question. Any other questions? Okay. So last time we talked about, so the hash index was the new index type that we talked about, and we did that real quick, and then talked about our join algorithms, and in particular the 3 different join strategies, the nested loop join, and the hash join, and the merge join. And then it talked real briefly about join order issues. And basically we just said that we'll leave this up to Postgres' query planner to handle that for us. And if it's doing a bad job, then it probably means you need to run the analyze command. We started talking about some of the limitations of the B-tree index with this as our sort of key example query. But this is an example of doing some sort of full text search where we're looking for the string corona that appears anywhere in the text field of a tweet. And we saw that the B-tree is just not suitable for that. And so today we're going to talk about a new index type called the GIN index that will be suitable for that, and how you work with that in Postgres. We'll also talk about, I guess before starting the Postgres specific stuff, talking about a little bit bigger picture with full text search outside of Postgres. And I think we'll have time today to go over the homework assignment as well. Yeah, the homework assignment's very similar in format to all the other homework assignments that we've seen so far, but it does have a few slight differences that that I will want us to talk about. Okay, so first, the full text search FTS outside of Postgres. And I think I mentioned this last time, there is no sort of SQL standard for full text search, the same way there is for like the like operator for normal text search. And so every database system has its own unique way of doing this. As far as SQL databases go, so relational databases, RDBMSs, Postgres is like far and away the most advanced when it comes to full text search. But there are other NoSQL databases that are specifically dedicated to full text search. The first thing that you should know about those databases is that they provide no ACID guarantees in their transactions. So in particular, if you have a server crash, then you're going to lose data. And at scale, so we've been using the Instagram example. Servers crash at Instagram all the time because they're so big, and it's just guaranteed at large scale no matter what you do, so data loss is guaranteed. And for most applications related to full text search, this is actually not too bad, that no one will notice if you're missing a few documents in your search results. Like if you go to Google, do a search for something, and I don't know, they have 1 million documents there, come back as your results. If it's missing 1 or 2 of those, almost certainly not going to notice. So this is in contrast with other applications where data loss would be like really unacceptable. And so because of this, like if somebody was using, so I've been talking about MongoDB as a NoSQL database, one that I particularly dislike because it's sort of well known for losing data. When we were talking about ACID transactions before, I brought up the example of The Guardian, the website used to use MongoDB, but they transitioned over to Postgres. And that's because if they were to lose like some of their articles, that's just unacceptable to them. That if you visit a URL and it just doesn't exist. But if you were to search for something in The Guardian and it just doesn't bring up one of the search results, that's not too big of a deal. That's a data loss that we could live with. So other applications, this is a really bad thing. Full text search, not quite so bad. Some examples of these other full text search engines. The most popular is Elasticsearch these days. And it's fairly powerful, probably like the most powerful currently existing full text search engine that's easily available or open source. Doesn't really compare even remotely though with say the features that Google or Bing or Baidu have, that essentially all of the research, like actual good research on full text search, is locked away in these companies and they don't make it public. The main disadvantage of Elasticsearch is you can't combine it with other SQL queries at all. And so yeah, it's a potentially very large disadvantage depending on what you're trying to do. Another fairly serious disadvantage is it requires actually installing it. With Docker, that's not too bad because you can just get a Docker image for Elasticsearch, but somehow you then have to actually get the data into Elasticsearch. And so if your data is in Postgres, you have to configure Postgres and Elasticsearch to talk to each other. There are like tools for doing that. ZomboDB is an extension to Postgres that connects to Elasticsearch for you, but it's kind of a pain in the butt. I've tried to do this and I have never successfully gotten it to work. So so that, I guess that's the main practical disadvantage from my perspective of Elasticsearch. Another disadvantage, which has sort of been all over the programming news recently, just in the last couple months or year or so, is that Elasticsearch is no longer open source. It used to be open source. It was originally developed as open source under the Apache 2 license. This is one of the I'd consider in like the second tier of famousness of open source licenses, that the 2 most famous licenses are the GPL and the BSD/MIT licenses. BSD and MIT is basically anybody can do with your code whatever they want to do. GPL is if you use the code, you have to contribute it back. Apache 2 is sort of somewhere in the middle of those 2. And Elastic, the company, sort of made this promise to the community that Elasticsearch, the program, is going to be under the Apache 2 license indefinitely in order to attract both developers to work on the project for them, essentially for free, not being paid by the company, and to attract users because users like having open source software. And this was a very successful strategy for them. The company, I'm not sure exactly what their market cap is, but a couple of years ago it was $2 billion. So it's a very successful company. And a lot of companies follow this sort of model. But then recently, Amazon started offering Elasticsearch as a service on AWS. So you no longer had to purchase from Elastic if you wanted somebody to manage your Elasticsearch instance for you. You could get Amazon to do it. Elastic, the company, didn't like this, so they relicensed Elasticsearch under this license SSPL. This is a license that was first created by MongoDB, and the basic gist of it is it doesn't allow third parties to host the software in a paid solution. So it's basically SSPL is Apache 2, but Amazon's not allowed to make money off of it. Because of this restriction, the Open Source Initiative, which is one of the main bodies for open source software, basically determines which licenses are compatible, not compatible with each other, things like that, has determined that this is not an open source license, and so both MongoDB and Elasticsearch are no longer considered open source projects, even though you can access the source code. So we would call them source available projects rather than open source projects. And in response to that, Amazon has forked Elasticsearch and will continue developing of their forked version and offering it on AWS. For a lot of projects, let's see, so forking like this happens a lot in the open source community. And basically, both branches of the fork are not going to survive long-term for, or that's historically what's happened. Both branches of the fork are not going to survive long-term. And so it's a sort of a business competition at this point between Amazon and Elasticsearch about which version of the software is going to win. I think a lot of people in the community, well, I guess depending on who you ask, they might support one company or the other in terms of, oh yeah, Elasticsearch has the right to be the only person to make money off of their software, or Amazon has the right to actually use open source software the way it's supposed to be used. But either way, there's uncertainty in the community about which one of these versions of software will be the main one, say 5 years from now. And so I think there is a maybe a reluctance for people to start new projects using Elasticsearch because of this. That said, if you were using Elasticsearch to build a search engine, nobody would think that's weird. Everyone would think that's okay, that's a normal thing to do. And there's lots of companies right now that use that. Lucene and Solar are two other projects similar to Elasticsearch. Elasticsearch is actually built off of the back of Lucene. And they're both sort of also popular solutions to full text search. And again, nobody would think it's weird if you're choosing one of these for a full text search engine. Out of these databases, Groomga would be my favorite. So other than Postgres, it's the only one that I've found useful for me in sort of actual applications. And the main difference between Groomga and these other ones is it's an embedded full text search engine. So it's just a library that you can include in your other projects and use it really easily. You don't have to spin up a whole other computer, whole other database system. And so if you're, say, not using Docker, then there's no need to start using Docker just to get your project to work. If you were developing, say, an app for Android or iPhone, then Groomga is something that you could incorporate into the app really, really easily to get a really good full text search on the document, say, on the phone. But these other systems can't really run Docker on an iPhone or an Android. So they're just a little bit harder to set up. Groomga in particular has good Asian language support. So the developers of it, the primary developers are Japanese. So it's got good support for Japanese and adjacent languages. That's the particular use case that I've found for it is for Asian languages. You can also incorporate it into Postgres fairly easily. There's an extension called pgroomga, and that's super easy to do. But again, you don't have ACID guarantees on the full text search parts. So you will occasionally have to rebuild your index if the server crashes. And there's also some weird things about it doesn't respect Postgres settings sometimes. And so there's some rough edges, but can be done, and that's not too bad. In this class, though, we'll be focusing on full text search and Postgres. And as we talk about that, we'll also talk about the general theory of full text search, and so that general theory will apply to all these other database systems as well. But we'll be focusing on Postgres. And so some of the main advantages of Postgres, you can still use your full SQL capabilities, joining with other tables. You can include other information inside of the tables besides just text. So you easily incorporate things like PageRank or dates and do searches on those as well. And again, Postgres' full text search is much, much better than other relational database systems. I don't know too much about full text search and SQL Server and Oracle, but in MySQL, MySQL is basically only English language support, and even then, like, doesn't actually do very good English language support. And MySQL, the way it does it, it requires you to use even more disk space than Postgres and these other systems. Some disadvantages of working with Postgres. So we've seen this first one a little bit before, that the tables and the indexes must be stored separately, that it's impossible to have a full text index without a corresponding table. And so that means that you do have some duplication of your space. You use about 2 times the disk space when you're using Postgres as opposed to, say, Elasticsearch. And Elasticsearch and all of these other systems that I mentioned above, they only store the index because that's all they do, is they index text. And so there is no duplication of a table and an index. So the database itself doesn't store this extra information, but it's still standard practice to store the raw information somewhere so that you can rebuild the index when it eventually loses the data, like it's guaranteed to do, because it doesn't have these asset guarantees. And so you're still sort of paying the price of having that stuff stored somewhere, but it's not in the database. So people will say that it uses less disk space. Postgres is a little bit slower on the inserts, update, delete operations because it has to touch the index and the table pages, whereas Elasticsearch only has to touch the index. But this is something that's also under active development, and there'll probably be alternative solutions in one of the next 2 versions of Postgres. We're currently on Postgres 13. By 14 or 15, people have been talking about the changes that need to be made for this to happen for a number of years now, and they're pretty close to getting those incorporated. So my guess is that definitely by 15, this will not be something that you'll have to worry about in Postgres. So Postgres doesn't support as many ranking algorithms as something like Elasticsearch does, because that's all Elasticsearch does is ranking things. But again, there's lots of active development to fix this issue. And we'll see in a little bit, there's this library pspacey that I've been working on that it actually makes Postgres support more languages than any of these NoSQL solutions do. I think Elasticsearch is the most multilingual of these open source full text search engines, or source available now full text search engines. And it supports about 30 different languages. With this pspacey library, Postgres supports 72 different languages. So it's a considerably broader set of languages. The other NoSQL sort of libraries, I'd say English is definitely their #1 priority language, and the other languages are sort of an afterthought, with the exception of the Gurunga system, where Japanese is their priority language, and then Chinese Korean, the secondary languages at similar level to Japanese, and everything else is just kind of an afterthought. But my hope with Postgres, especially over the coming years with this pspacey library, is that it's sort of like every language is going to be on an equal footing and not prioritizing English over these other languages. So quick recap of some other things, JSON related things. We talked before about that Postgres does now support JSON B type for including JSON in the table. That wasn't always the case. It was 2016 actually when that was first introduced. And MongoDB and Cassandra and all these other NoSQL for JSON solutions, they were really becoming popular in 2012. And so at that time, these solutions would have been like something that you might want to choose over Postgres. But now that Postgres does everything that they can do, certainly my recommendation, and I think the recommendation of a lot of people, is you never want to touch these if you don't have to. Just stick with Postgres. Because it does everything they do. It's faster, it supports ACID transactions, blah, blah, blah. And I think a similar sort of thing is going to be happening with full text search in the next, say, 5 years or so. That right now there's all these other alternative NoSQL solutions for full text search, but full text search in Postgres is on a rapidly improving trajectory. And so my guess is that 5 years from now, once this Amazon versus Elastic debacle has sorted itself out, it'll almost be a moot point because you can get everything and more from Postgres. Let's see. So these days, I'm pretty much up all night holding my 2-week-old son. And this past night, I was watching this video right here. And basically what I've been doing to entertain myself at 2 a.m. is watching videos about Postgres from PGCon, a conference on Postgres developers. And this is the, this video is about like the details of JSONB and the history and the future of it. And this is the guy who's the implementer of it. And so I like seeing pictures of people who are like driving forces behind different aspects of software I use. So that's him. Yeah, so at this point, so my opinion is that Postgres is definitely the way to go for full text search in a new project. But full disclosure, that's not like a settled opinion on that everybody has. I think Postgres over MongoDB, that's a pretty widely accepted thing now, but Postgres for full text search, that's still up in the air. So definitely nobody would think it's weird if you chose to use Elasticsearch or Solr or Lucene. Certainly if you're going to a company after graduating and they have some sort of full text search engine, it's almost certainly going to be with one of those other systems and not with Postgres. But people who work with Postgres would say that this is the way to go, and that Postgres has a good future for it for full text search. Let's see, before we talk about the details in full text search in Postgres and the mechanics of it, are there any questions about sort of like the broader big picture, how things in the community fit together? Okay, so now to the technical details. So first of all the basic theory we'll discuss will apply to all of these full text search engines, doesn't matter which one it is. Today we probably won't get to too much of this theoretical stuff, and that'll happen on Monday. And today we'll just focus on the mechanics of like how you actually get things to happen and seeing that it does make things a lot faster. And we'll start our discussion with just English text, since we're all familiar with English, and then we'll talk about non-English text after that. And there's two important types that we'll be getting familiar with, this TS vector and this TS query. I just want to highlight, first of all, that these are really complicated types, this TS vector and TS query. And so today in class, we'll go over just some of the high-level sort of intuition behind them, what you should be thinking about when you read the documentation. But you probably will need to reference the documentation for your homework assignment, this Twitter Postgres 2 assignment. And that's intentional. I'm intentionally not going to cover all the little details that you'll need so that you'll be forced to get some experience reading the documentation about this. Okay, so there's yeah, what TS query and TS vector and TS query represent is TS vector is sort of like the document, the thing that you're searching for. So on Google, every web page would be represented by a TS vector. And then a TS query is your search conditions, the thing that you type into the search bar in Google. And there's two different ways to create these TS vectors. This method right here, which takes a string and the : operator in Postgres. I'm not sure if we've seen it before explicitly or not, but what it does is it casts or changes the type of the thing on the left to the thing on the right. So this converts this string into a corresponding TS vector. And then there's also this function that does the same thing. So I'm going to switch our screen over to a Postgres terminal so that we can go ahead and just see exactly what these TS vectors look like. And currently I'm in our the Twitter Postgres sign-in, and I'm in particular in the number 2 version. That's the homework for this week. But basically everything's the same. And I'm going to paste that first command right here, and this is the output. And what you can see is that when you cast this to TS vector, the TS vector just essentially tokenizes this string up here, separating it out based on their spaces between things. And so there's 4 different words in here, 4 different things inside of this TS vector. Each one of these things is technically called either a token or a lexeme. And there's a subtle difference between exactly what a token and a lexeme is from an NLP, a natural language processing standpoint. But for our purposes, they're going to be the same thing. And it's just essentially one of these words inside of this string. You'll notice that these words are also not in the order anymore that they appeared up here, that they're in alphabetical order, which is going to be important for efficiency reasons later on. Let's come back over here and just see what this toTS vector function does. Paste that right here. And there's 2 important differences that you can see from this, this output. When you just cast like this, then every word gets contained in the TS vector. When you use the toTS vector function, the toTS vector function is language aware, and the default language is English. And it's going to remove words that are called stop words, which are words that are just very common in whatever language that you're working with. And so nobody's going to do a search in a document for getting all the documents that contain the word this. That's just, if you're searching in English language, that's not a very meaningful search. And so for efficiency reasons, it makes sense to take out these stop words. If you really wanted, for whatever reason, to be able to support searches for stop words, like you wanted to do some sort of linguistic analysis where you want to compare how often is the word this used compared to the word that in different texts, then you'd have to use this sort of manual conversion and not use the toTS vector. But this is the standard way to do it. This is the 99% of the time what you want. The other thing that you'll see is happening with this toTS vector is there is a recording of the location inside of the string where a particular word occurs. So here it says test:4 because test is the 4th word in the string. And if I were to change this to say this is a test and an example like this, then you can see we have test and example right here. These are the 2 sort of main words inside of here that that are the important words to pull out, and they have their corresponding locations 4 and 7. You'll also see that the word example over here has been what we call stemmed. So example, that in quotation marks, has been stemmed into the lexeme example. And what stemming means is just converting a word into some sort of standard base form. And here, let's copy and paste it like this. Oops. If I were to change this to be plural examples like this, you'll see that we get the same result down here. And this is just to ensure that if we are searching for example or examples, then we get the same thing. Any questions about the TS vector type? Okay. So then here is a query on how you can actually use this full text search. So selecting from the text in tweets, so getting the actual text that's been sent, and then here is our where condition. So here to the left, we have the converting the particular text column into a TS vector. And then we have this double at operator, which you should think of sort of like if you're pronouncing it in your head, you should pronounce it as contains. And then this query operator to the right. And if we go ahead and copy and paste this over here and hit enter, and at this point, you can see that it's not returning an answer for us instantly. And that's because I don't have any indexes that are suitable for this query. If I were to let it run for the entire time, it would take about 1.5 minutes or so to run it. I'm going to go ahead and create this index for us real quick. This index will take also about 1.5 minutes to run. It turns out to take about the same amount of time to create an index on a full text search as it does to just do the text search without an index. So I've never seen an application where somebody would want to do a search, full text search without an index. For other searches like equality searches, greater than, less than, there are some situations where an index is not going to help you. And so you might not want to create the index. Creating it would just slow you down on your inserts, updates, deletes. But for full text search, you basically need to have an index to make it worthwhile. The syntax for creating this index, so again, it's a gin index. And anytime you're using something other than a B tree, you have to use the using, then the name of the type of index that you're creating. And in this case, well, actually in every case, in order for Postgres to know to use an index for your particular query, the thing to the left of whatever the operator is, so in this case, we have this double at operator, this contains operator, the thing to the left of that must be one of the columns inside of the index. If it's not one of the columns, then it can't be used. So we don't just do a gin index on text, we do a gin index on this function right here, which converts our text into the TS vector for us. Here, this English right here just enforces that it's the English language processing that we'll use. And we could change it to Spanish or something else by just changing this right here. So let's switch back over here. Okay, it's still taking, it's not quite finished yet, creating this index. So hop back over here for a second. Yeah, we'll start talking about what this index actually looks like, what it does, this GIN index. So GIN stands for a generalized inverted index. Let's see, in the documentation for the GIN index, they specifically say that it's not inspired by gin, the drink, the spirit, the alcohol, and you should be thinking of gin as in genie because it's magic and is going to make your searches happen really fast. we'll see that this GIN index has a few limitations, and this GIN index has been sort of, in some sense, superseded by this RUM index. The RUM index does everything the GIN index does, plus a little bit more. So for some applications, most applications, it's the right one to choose. This RUM index was created by not the Russian that we saw earlier, but his team was the one that implemented it. And they specifically said that we think gin should be the drink and not the genie. And so we want our rum index. We chose rum to follow the drink theme rather than picking some other mythological creature. Okay, so we've created our index now. It took 2 minutes and 20 seconds. So the data that it did this over is 1 day's worth of tweets from the data set that you did the MapReduce assignment on. And so it did sort of all of the processing that your MapReduce program did, plus more. It created this index that we can now do these searches on, which we'll see here in a second. But what I want to highlight at this point is that if you recall from your MapReduce assignment, the fastest that your map.py function would have ever run was 5 minutes or so. If there was sort of best case scenario, no other people using the Lambda server, and you weren't running any other map.pys, just one at a time. The creating an index on one of these files after it's been loaded is about twice as fast as that Python file was. So creating these indexes is really fast, just as fast as, or even faster than doing the MapReduce procedures. So yeah, there should be, like, from a computational perspective, it shouldn't be like a scary thing to create this index. In some sense, you're doing a lot more work. You're doing a lot of pre-processing to making these other future queries so much faster, but that pre-processing is the same amount of time that you'd have to do for the actual processing anyways. Okay, so now I have this same query right here. I'll go ahead and hit enter, and there we go. So it took a little bit of time to calculate this. And you can see it's just bringing back all of these tweets, but it wasn't really like very much time. It would have previously had to do the full scan of the entire table, taking about 2 minutes. Now we're down to just about 2 seconds. If I rerun this again, you'll see that it's even faster now. It went from 2 seconds the first time I ran it down to 200 milliseconds the second time I ran it. And that is typical behavior of really any index in Postgres, but especially full text search indexes, is that the first time you try to use it, it's going to be slow, but subsequent times it's going to be faster. And this is related to that caching algorithms that we were talking about a little bit on Monday. And the idea is that when we first have to use this index, then the index is sitting entirely on disk, and so we have to access that disk, and accessing disk is slow. But we had that shared buffers parameter, the shared buffers parameter. Let's go ahead and display it. And this shows how much space in memory we're going to reserve for pages, whether they be index pages or table pages that have been recently accessed. So when we access them a subsequent time, we don't have to access the physical hard drives. And so the first time we did this query, it was slow because everything was on the hard drive. The second time it was fast because it fit inside of the shared buffers. Let's see, let's go ahead and do an explain on this. And you'll see down here that we're using a bitmap index scan on this index that we had just created. And so that's why it's coming out faster. Previously, it was having to do a sequential search over the table. let's come back over here. Yep. And we'll talk, yeah, let's do the actual implementation. Like what is this gin index doing under the hood for us? That'll be our next step. I'll be visiting this web page right here to actually look at some of the pictures that they have, and following through their pictures. And so if you want to revisit this topic, get a more detailed understanding, it'll be hopefully easier to follow along with their write-up. Before visiting this page, though, are there any questions about anything that we have seen so far?
I had a question about the speed.
Mhm.
So if it takes 2 minutes for one day's tweets to get indexed, then wouldn't it take like a few hours at least to index all the tweets from last week?
Yeah, so that's a great question. So yeah, the question is like, what if we didn't want to index just a single day, but we're indexing that entire data set of tweets? How long is that going to take? And the answer is that it's going to take definitely a lot longer time, but it should still be faster than your map reduce procedure was. That the map reduce took 5 minutes per day, and so it was roughly on the order of 4 to 5 hours for the entire data set. Again, assuming that there's no other resource contention, nobody else is using the Lambda server. This creating the gin index took about 2 minutes per day, so it'll complete in about half the time. It'll be a little bit more than half the time because inserting the last days will take a little bit longer than inserting the first days due to the, we'll see that building a gin index is going to have in login sort of behavior. So that login factor will catch up with you a little bit, but not too much. The one subtlety about this is that you'd have to specifically enable parallelism for the index to be created in parallel. So yeah, this is Postgres 13 that the Docker images we have are using. The latest versions of Postgres have parallel index construction support built in. So this gin index could be constructed in parallel. And so if you set it to use 40 parallel workers, then it'd fully use up the Lambda server and you'd get the same sort of good parallel speed up as you got with the MapReduce assignment. Did that, Savik, answer your question in there somewhere?
Yeah.
Good question. Any other questions?
You said that when like the server crashes, these indexes are lost because there's no ACID guarantee. Does that mean you have to recreate the index and spend all of that time again before your service is functional again?
That's a good question. So this gin index, it's native built into Postgres, so it does have the ACID guarantees. And so if the server crashes for whatever reason, there's no need to do anything. You'll still have the index, it'll still be working, and it'll still be lined up, contain all the information that the table contains. It's only the non-Postgres solutions that don't have the ACID guarantees. So Elasticsearch, Lucene, Solr, Grunga, those systems, if they crash, then you'd have to redo this 4-hour process. And it'd take approximately the same amount of time for any of those systems to do this. Some of them might be like on the order of 10 to 50% faster, but nothing like significantly more than that. Good questions. Any other questions? Okay. So let's switch back over here and we'll take a look up here. This is again that web page on haber.com, that Russian web page. Again, the team who first actually, I don't know about who created the gin index first, but the team who did the rum index, which builds off of the gin index, and the people who are explaining this is all from that same Russian group. So that's why the documentation is on a Russian webpage. So up here are some SQL commands that they're giving, which is building an index for doing full text search. The main thing right here is just to look at these text documents that they're inserting into their table as examples. It's just this tongue twister thing. The tongue twisters happens to be a useful example because you'll have the same word appearing multiple times in multiple documents. You'll have, so like slitter and slit, depending on exactly how you decide to do this, this stemming process, you might combine these into the same lexeme, or they might be separate lexemes. And then you have these words like a and can, and that are going to be stop words that'll be removed from the text. I don't think I mentioned this before, but the punctuation will also be removed from the text and not something that you can search in. If you are, and that's when you're using this toTS vector function. If you really wanted to be able to search on punctuation, for example, if you were creating a search engine for source code where punctuation matters, then you would not use the toTS vector function. You would use the casting a string to a TS vector. So that's the main thing to notice here. The next thing is that in their table right here, they have two columns. The first column is a text column. So this is what they're actually loading into their database, the thing that we're going to be doing the full text search on. And then the second column over here is a TS vector column. This TS vector column is a little bit different than the example that I showed on our class webpage, because in our class webpage, in the actual creating an index right here, I put the toTS vector function inside of the index column. In this example, they're not doing that. They're simplifying the index creation part by creating a second column. And then here in the update command right here, they're setting this TS vector column to be the toTS vector of the document. So they're doing the same thing that I did in the notes. They're just doing it in a slightly different way. And it'll turn out that for the 99% of use cases, both of these methods will have the same runtime overhead, same runtimes in the gin index. But this method is going to use up more disk space. So you have to basically store the document as actual text and then store the document again as a TS vector. And the TS vector is going to be approximately the same size as the text because it's the only thing you're removing are these stop words. And so it might be half as big, but it's adding an additional factor of overhead if you do it this way. So yeah, a lot of resources do things this way because in older versions of Postgres, you were not allowed to put functions inside of indexes. And so this was how you had to do full text search, but now you can't put functions inside of indexes. So that's what I always do. Okay, now let's scroll down to see a picture of what the actual gin index structure looks like. And this is a moderately complicated data structure, probably the most complicated data structure that most of you have seen before. And so we'll spend a little bit of time looking at this picture and making sure we understand it. So the first part of this picture to understand is the square blocks up here. And this part up here you should think of as a B tree. It is in fact a B tree, a B plus tree. And each one of the entries in this B plus tree are the lexemes in the TS vector documents. So here we see things like slit and slitter. So those were two words that we saw in the document, and they appeared down here. And then you see a lot of other words appearing down here, but not all of them because some of them stop words got removed. So what the purpose of this B tree is for is that when we have our TS query and it has whatever words are inside the TS query, we can quickly find the locations in this B tree that correspond to the TS query. Now we need to talk about what these black boxes are. These black boxes are represent the tuple IDs, the TIDs of the documents that contain each of these words. So here, if we look at the word good, there's only one document that contains the word good. That document sits in tuple 1, 2 inside of the heap table, or the heap pages, or the table pages. All of those, again, are just synonyms for the same thing, the pages that store the information for the table. If we go back up to the documents up here and read through it, we would see that only one of these documents contains the word good, this one right here, and none of the other ones do. So if our TS query was for the word good, then it'd be really easy to get the document back that corresponds to the word good. Just do our normal B-tree search, find the word good, and we're done. Here's the list of all the things that we need to return. This list of things, so you see most of these have just one entry inside of them, but here's one with two of them. They're called the posting list. The posting is the set of elements or the set of documents that contain whatever these words are up here. So there's only one document that contains the word good, so there's only one element in the posting list. The word sit, there are two documents that contain the word sit, so the posting list has two elements inside of it. When the posting list grows to be too large, and that what too large means is something that's configurable, but not something that you really need to touch or worry about, the posting list converts into a posting tree, and that posting tree is stored as a B tree as well. So the here for the word slit, there are, 9 documents that contain the word slit. And so the B tree contains 9 elements inside of it. It's important to keep these two different B trees separate in your mind. That we have one B tree for searching, actually doing a search on the documents themselves or the lexemes themselves to find the corresponding documents. And then we have a second B tree in the posting tree as an alternative to the posting list, which gets created when the posting list is too large. In our coronavirus example, when we did the search for coronavirus, there were a large number of documents returned related to coronavirus. So my guess is that the coronavirus would be stored as a posting tree in the corresponding GIN index. Are there any questions so far?
So these I don't know what they're called, like coordinates of the the two numbers.
Inside black here, these are tuple IDs. So the first number is the page that the tuple is located in, and the second number is the index in that page, the particular tuple in that page. Sorry, I cut you off.
Okay.
Go ahead.
Okay. Yeah, so no, that was my question. Like, what did the two numbers refer to? That makes sense.
And these tuple IDs, they're the same things that get stored in a normal B-tree index or a hash index for whatever that search term is. So here, this B-tree index is very, very similar to just a normal B-tree index created over the same field, But the difference is that instead of the document itself being each one of these white boxes, each one of the entries in the B tree, instead of having the document be the entries in the B tree, we have each of the words from the document be an entry in the B tree. Otherwise, it's exactly the same data structure. Good question. Any other questions so far? Okay. So next we're going to talk about like why do we bother putting things inside of posting tree like this? And in order to answer that, we're going to first go back to Postgres and modify our query just a little bit. So I'm back over here, and here is the same query that I had before, selecting the text from tweets, matching this condition. So specifically looking for words mentioning coronavirus. But maybe I don't want to just look for coronavirus. I want to look for coronavirus and something else. So let's try coronavirus and Trump like this. And we get back a bunch of results that mention both coronavirus and Trump. And you'll notice again that this happened really, really fast in just 40 milliseconds. What's happening here is first we're going to find all the documents that contain coronavirus, and then we're going to find all of the documents that contain Trump. And then we're going to, once we have those two sets, do an and between those two sets to only get the intersection. So if we come back over here, if we see, let's say we wanted slit and sit, then we would find sit, get these two items right here, 1, 1, and 2, 3, and we would find slit right here, getting this list of 9 items. And then we would have to join this right here with this right here on this condition that the entries be contained inside of both lists, or this list and this B tree. So here we have 1, 1 for sit. There's 1, 1 down here, 2, 3, 2, 3 down here, and so our result for sit and split would just be these two elements right here. The fact that this is a posting tree, an actual B tree structure, means that I can do this search inside of this tree really, really efficiently using our normal B tree find operations. Since this is small, we would just search one at a time and to get that they're both in there. If it was a posting list, each search would be an O of n linear time operation, but since it's a posting tree, each search is a log n operation. They have if we scroll down a little bit further, they have a diagram that illustrates this. So here they search for the word Manny and Slitter. I think they show the actual query. Example of a query, here it is. Manny and Slitter, right here is their query. And query plan, bitmap index scan, and here Manny 02, Slitter, this tree right here, and then it does the bitmap and between this and this. Because they're when we're doing a search on one of these GIN indexes with full text search, because there's going to be multiple either lists or trees, multiple posting sets that we're going to have to combine together using an and or an or, depending on what the person types in the query. Here I typed in and, but we could easily type in or to get a different query. The type of index scan is guaranteed to always be a bitmap scan. The GIN index does not support an index-only scan, and it does not support an index scan. It only supports a bitmap scan. If we come back over here and do this explain, you'll see that here we're getting the bitmap index scan for all of these conditions. Are there any questions about why this is a bitmap scan or how the what that bit mapping procedure looks like?
Why is it quicker to do 2 searches for 2 different words instead of just searching for both the words in each document? And then only going over them once instead of going over them twice?
So in the scan procedure, we are only going to go over them once. So if we're searching for many and whoever, then when we search for many, we get this red set right here, and we search for slitter, we get this red set right here, and that's the only time we touch this B tree up here. So we only touch this B tree once, but then once we have these 2 red sets of possible candidates, possible things that might match our search condition, we have to combine them together with either the and or the or condition. And it's that combining together that will search through this second level of B tree, the posting tree, but it doesn't search back through this B tree up here at all. So there's 2 B trees. Each B tree will only get touched once.
I see. That makes
Good question. Any other questions so far? Okay, let's come back to our notes. And so the GIN index is used for, so full text search is sort of like the main biggest application of it. It's also used for indexing JSON-B objects or arrays. Basically anything that is contained out of other parts, you can use the GIN index to make those searches faster. For full text search, it's always this @ operator, but it also supports these other 2 operators right here. And I want to do a quick example with arrays to illustrate what that looks like. So I'll come back over here, and if we look at our /d tweets, recall that, so this is the schema for tweets. Here is our array for withheld in countries, and the semantics of withheld in countries is that these are countries that for whatever legal reason the tweet is not allowed to be displayed in. From tweets like this, and currently there's no index on it, so it takes a long time to run. Also, since it's an array, what we want to do is, or what we've seen before of how you actually get the entries out of an array, is that you use the unnest function like this. And there we go. So here is our results. I believe on the tweets table, let's see. Yes. So here is the query, and here is the results. In order to, if we wanted to create an index on this right here, you might think that, okay, here's a function, so we can create an index on this function, but we can't do that because this is not a normal function. It's a set returning function, and you can't create an index on a set returning function. There's no way, for example, to, if we had select unnest tweets in countries like this, if we wanted to have unnest withheld in countries, only searching for ones withheld in Germany, DE is Germany, like this, that's not allowed because an unnest is not allowed inside of a where clause. And the only time we can use an index is when the thing indexed is to the left of an equal sign. So in order to be able to create an index for an array like this, what you do is you don't use the unnest function. You use this at greater than like this. And the semantics of this is that here we have an array on the right, an array on the left, and that this array on the left is greater than this array on the right, which means that it contains all the entries that this array on the right contains. The at greater than and at less than are used for when the sort of the containers that you're comparing against each other are the same type. So here it's an array on the left and an array on the right. And you use the at operator when it's two separate containers. So for full text search, let's go back up here to full text search. The reason why we use at is because we have TS vector on the left and TS query on the right. For full text search, we need to have two separate types because the TS query is going to be able to do these ors and these ands and these more complex conditions for us. And that's not something that we want contained in the TS vector. For TS vector, if there's ands and ors and any of that punctuation inside of the text, we want it stripped out. So that's why we have two distinct types. For arrays, you always use the at greater than, at less than. For full text search, you always use at. And for JSON, you can use any of these three combinations. In your homework assignment, the Twitter Postgres 2, you'll have to create some JSON-B indexes and rewrite some queries using these operators right here. So I'm gonna leave that for you to look up in the documentation on exactly how to do that. But when we talk about the assignment, I'll show you the spots where you need to do that at. So the limitations of this, these elements inside of a GIN index, they'll never get deleted. So if we come back over here and let's say we deleted the document that contained the word many, the word many would still be contained in this B tree up here. It would just have an empty posting list. Yeah, so that's just something to be aware of, that if you have a heavy update or delete workload, then your index might grow in size. But it's not typically an important thing. This one here, though, is really important. The GIN indexes are slow to modify. And let's think about why that is. Well, so we've talked about B-tree indexes before, and B-tree indexes are fast to modify. That you do a quick search and you just update it. Login time to find the location. The problem with a GIN index, though, is that when we add one document, it does not add one entry into the tree. It could add thousands or tens of thousands of entries into the tree, depending on how big the document is. And so that means that the entire tree is potentially going to have to be restructured significantly for every time you insert a single document. The GIN index offers both a slow mode and a fast update mode. And in the slow update mode, it actually does that update every time you insert just one thing. It completely changes the tree. In the fast update mode, it keeps a separate list that batches up, say, 100 elements at a time and inserts all 100 at once, so that if two documents both contain the word many, you don't have to repeat the work of finding the word many in the tree. And that's the default. And but just keep in mind that you never want to create too many indexes. They always slow down your inserts and updates and that stuff. But a GIN index will really slow it down if you create too many of those. Let's see. I want to talk about our homework just a little bit. So we'll continue talking about these limitations next time. And we'll jump up here to the top to the Twitter Postgres 2 assignment. And so the format of this assignment is very similar to the previous assignments that you've had with SQL folders and expected, and you'll run the check answers to do this. But now there are two separate folders, one for the normalized database and one for the denormalized database. And you will have to create separate queries, have separate queries for both of these databases. I'm giving you the queries for the normalized database. So there's 5 queries here. I'm giving you what those queries are. They're just doing things like you did in the MapReduce assignment, like counting the number of tweets that have hashtag coronavirus. But some of the other ones are a little bit more complicated. And the first thing that you'll have to do is, for these queries, create the appropriate indexes so that these queries run fast. The normalized database running all 5 of these queries takes about 25 seconds for me with no indexes, and it takes about a second for me with once you've created the indexes. So that's the first step. And then the second step is I actually have not provided you any of the queries for the denormalized database. And so you'll have to both create good queries for the denormalized database and create good corresponding indexes for the denormalized database. I have some hints about how to do that down here. So step 3, creating queries and indexes for the denormalized database. In my solution, I use 3 GIN indexes and no B-tree indexes. 2 of these GIN indexes are on the just the JSON B blob itself, doing fast search into the JSON blob. And again, that's the location where you'll have to use that those @ operators on the JSON blob. And it's possible to do it correctly and quickly with either the @ or the @ greater than, @ less than solutions. And then the second GIN index will be an index for the actual full text search in the database. For the normalized solution, I have 3 B-tree indexes and 1 GIN index for the full text search. The submission for this assignment. So this assignment's using only a single one of these Twitter data zip files. So it's only about 4 million tweets. But this is still too much for GitHub Actions. They'll complain if you try to upload and do all of this work on GitHub Actions instead of doing it on the Lambda server. So we're not going to use the GitHub action test cases. Instead, what you'll do is you'll run these 2 commands down here. They'll generate these 2 files, results.normalized and results.denormalized, which contains the same output that you would get if you had done it through GitHub Actions like we're doing before. You're just going to do it manually on the Lambda server to create these files. And you'll add these files to your GitHub repo and push the repo to GitHub. And then when I'm doing the grading, that's what I'm going to look at, is the results of these files here. Your grade's based in 2 parts, both on the correctness of your denormalized queries, that they should be getting the exact same results as the normalized queries. And so we've had practice at this point of doing the creating lots of normalized queries, but you haven't created any of the denormalized queries yet. So it's important to get practice with that. And that's what this is grading for. But this is also grading for that when you're creating these queries, there are some versions of these queries that you can create good indexes for, and some versions that you can't create good indexes for. So if you look at the views from the original Twitter Postgres assignment, those views use the unnest function instead of the @ operators. And so it's impossible using the views that I've already given you to create an index that's going to work well. You'll have to rewrite them using the @ operators. And then the other points are from runtimes that if your runtime is over 2 seconds for normalized or 4 seconds for denormalized, you lose 1 point per second. Are there any questions about the assignments? What you'll need to do?
Why does it say that only the denormalized ones will have points?
Sorry, this should say denormalized here, and this one's normalized.
I think he's referring to point 1, and I think it's because you already provided us with the normalized queries. Oh no, sorry, not part one. Point number one, where you're assigning points.
Yeah. So there's two sets of queries, the normalized queries and the denormalized queries. I'm giving you the normalized queries as a reference, and then the denormalized queries are the things that you have to write. You should find writing I think the index is fairly straightforward for the normalized queries, and it'll be both writing the queries and writing the indexes for the denormalized will be the trickier thing.
I see.
Let's see, I think that's our time for today. So I'll stop our recording, and that'll be the official end of class. But if anybody does have other questions, I'll stick around to